Welcome. In this video, we take a look at analyzing circuits with multiple diodes. The specific techniques we can use are the ideal diode model or the constant voltage drop model. The example has three diodes. Let me bring that up. Okay, so the example has three diodes, and we can easily solve this. When I say easily, the easiest method is to use the ideal diode model. But we will use constant voltage drop model in this video. And then constant voltage drop would be the exact same analysis as the ideal diode model. It just requires addition of the diode voltages of 0.6 or 0.7 volts. So let's begin. So here in this circuit, we have three diodes, D1, D2, and D3. Each one of these is either connected to ground or to some power supplies. There are a total of three power supplies in here. We have a plus 10 volt at the top, minus 20 below on the left, and minus 10 below on the right. Okay. Now, when you're analyzing circuits with multiple diodes, the first step, or the first thing to do is to count the number of diodes. Here, obviously, it's very straightforward. We only have three diodes. But in real life circuits, of course, there could be tens of hundreds of diodes. And with each increasing diode, the complexity of the circuit increases, the analysis increases, because we are analyzing for one state of a diode at a time. So the total number of possible states in that circuit, meaning whether the diode is on or off, can be given by 2 raised to n, kind of like the binary number system. So in this case, there are 8 possible states. Okay, 8 possible states. All diodes could be either on, or all diodes could be off, or any combination thereof. We will analyze the circuit using the constant voltage drop model, right? And we are going to assume that VD is 0.6 volts. Now, that constant voltage drop, of course, depends on the diode that we are using. If it's silicon diodes, it's 0.6 to 0.7 volts. If no voltage is stated, you're free to choose your own. In this case, nothing is stated, but we are sticking with 0.6 volts. And if you're using germanium diodes, of course, the value is different. If it's gallium arsenide diodes, it's different. So again, depending on what kind of diode you're using, the constant voltage drop model would have a different voltage. Now, in this case, I'm going to start with all three diodes on. D1, D2, and D3 all have on states. And I'll explain the reasoning. Now, of course, these are all assumptions, right? The assumptions are based on certain logic. They're based on certain rules. Now, if I take a look at diodes D1, D2, and D3, if I pick, let's say, out of the 8 possible states, if I pick the 5th state, meaning, let's say diode D1 is on, D2 is off, and D3 is on, I might go through like 4 different analyses before I come to the right answer. Okay. If the right answer is the 8th possible state, I might have run through 7 different analyses before I choose the right one. So again, we don't want to do that. As an engineer, we want to work with maximum efficiency, of course. So we make our assumptions based on certain logic. So the logic here is, if I take a look at diode D1, D1 is connected to the minus 20 volt source. I mean, the cathode of D1 is connected to the minus 20 volt source through the resistor, of course. So logical choice dictates that if the cathode is connected negative, then anode is probably higher and the diode is forward bias. And hence I can safely assume D1 to be on. It could be, of course, wrong. We don't know. Then we go to D3. The anode of D3 is connected to ground, meaning it's held at 0. However, the cathode is connected to minus 10. So the cathode is negative or lower potential than the anode. More likely than not, D3 is also on. And again, at this point, we just don't know. And then we come to D2. Now for D2, the cathode seems to be connected to -10, and the anode seems to be connected to +10. Okay, so we could assume it to be on, but there's also the matter of this -20 volt connected to the anode of D2. So in this case, diode D2 could be on or could be off. Either assumption would be fine. We just don't know yet, right? This is an assumption. We just need a starting point. So we just choose D2 to be on, meaning all three diodes are on, and then analyze the circuit. From our analyses, if diode voltages are negative, then our analysis is wrong. For a analysis to be correct, for our analysis to be correct, diode currents need to be greater than 0. ID must be greater than 0. Here ID would be equal to 0 and VD would be less than 0. Right? If diode voltages are negative, VD is less than 0, then the diodes are off. Our assumptions are incorrect. So then this would mean forward bias. And this would mean, actually I'm running out of space, but this would mean reverse bias. Okay. So let's begin analysis. I've drawn out the circuit here with the constant voltage drop model. Each of these diodes is replaced with a voltage source of 0.6 volts that represents the voltage drop that is required to turn the diodes on. Remember, our assumption is that the diodes are going to be, our diodes are on. If they are on, then the diodes are dropping 0.6 volts across the anode with reference to the cathode. Okay. Now, D1 has a cathode that's towards the left. So minus sign is on the left. Okay. D2 cathode is on the right. So minus sign is on the right. And D3 cathode is on the left. So minus sign is also on the left. Okay. And that's how we have drawn up our voltage sources that represent the three diodes. The voltages are labeled as VD1, VD2, and VD3. Okay, and the currents, respective currents, are flowing from the anode to the cathode, ID1, ID2, and ID3. Okay. Reference for the diode voltage and the diode current always goes from anode to cathode. Also, I have labeled the three resistor currents as IR1, IR2, and IR3. Okay, IR1, IR2, and IR3. And let's see, one more thing is the nodes. The nodes have already been identified for us right here, A, B, and C. And of course, nodal analysis, going back to circuit analysis 101, any node voltage is always referenced with the ground or a specific reference point. In this case, it will be this point right here. Okay, A, B, and C voltages are referenced with that ground point over there. So now at this point, our circuit setup is complete. We would simply apply any circuit analysis technique that comes to mind to determine either the diode voltages or the currents. Now, of course, if the diode, our assumption is D1, D2, and D3 are on, meaning all diode currents should be positive, that would verify our claims that these diodes are forward biased. What we can do at this point is we can simply identify what the values are at each of these nodes, A, B, and C. So let's say A, the easiest and the simplest one to identify is node C, right here. And the reason is because one end of the diode is connected directly to ground. So node VC, when measured with respect to ground, would simply be minus 0.6 volts, right? Voltage, node voltages are measured with reference to ground right here on the right side. And so if there is a voltage connected directly to ground, we can simply write VC as minus 6 volts, minus 0.6 volts. Now, if VC is minus 0.6 volts, what is VB? Well, VB is 0.6 volts above C. And so VB is 0.6 minus 0.6 gives me 0 volts. So VB is 0 volts. And if VB is 0 volts, then VA, which is 0.6 volts below voltage B, would again be minus 0.6 volts. Okay, minus 0.6 volts. All right. So now that I have my node voltages, I can either apply KVL or I can apply KCL at each of these nodes and figure out what the current equations are and the values of these currents. Okay. So if I look at, let's see, my currents ID1 right here, and then I look at IR2, we see that they are one and the same, right? We can see the diode currents ID1 is the same as IR2. We can state that IR1, the current coming from the top, splits into two diode currents, ID1 and ID2. That is, of course, by applying KCL at B. And then we can also apply KCL at C to determine that IR3 is equal to ID2 plus ID3, right? So there's a whole bunch of equations we can use. So let's start with ID1 and IR2 because that seems to be the simplest. So if I wish to find IR1, I can simply take right here the voltage across the resistor R1, apply Ohm's law, and find IR1 that way. So IR1 would simply be 10 volts minus 0. That is the voltage across R1 divided by 10,000 gives me 1 milliamp. Okay, 1 milliamp. Then I can find IR2. IR2 would be node voltage VA minus of minus 20. So it would be 0.6 minus of minus 20 divided by 10,000. And that gives me minus 0.6 plus 20 gives me 19.4. 19.4 divided by 10,000 gives me 1.94 milliamps. 1.94 milliamps. And then finally, IR3. IR3 is the current flowing from VC to minus 10 volts. And so VC, of course, sorry, not VC. IR3 is the current flowing. Yeah, it's the current flowing from C to through R3, resistor R3. So I can write down the voltage as minus 0.6, which is node C, and minus of minus 10 divided by 10,000. And so this time it is 9.4, and so it's 0.94 milliamps. 0.6 minus 10 or minus of minus 10 gives me 9.4 divided by 10,000, 0.94 milliamps. Okay, so now let's calculate the diode currents. ID1 is straightforward, right? ID1 is directly equal to IR1, which is 1 milliamp. 1 milliamp is greater than 0. It's a positive value, right? So my assumption 1 is verified. And so let's assumption 1 is verified. At least you're on the right track. And then ID2, we apply KCL. We apply KCL at node B, I get IR1 is equal to ID1 plus ID2. And so ID2 is IR1 minus IR2, which gives me 1 minus 1.94, which gives me ID2 as minus 0.94 milliamps, which is less than 0. My answer is not valid. Sorry, not answer. My assumption is not valid. Okay. My assumption that D2 is on is not valid. All right, so we're going to have to go back and analyze it again. But let's finish up with ID3. So ID3 is going to be IR3 minus I. Let's see. Okay, ID3 is coming in, plus ID2 is equal to IR3. And so ID3 is IR3 minus ID2. And so I get 0.94 and minus of minus 0.94. And therefore ID3 is 1.86 milliamps, which is greater than 0. And hence my assumption that D3 is on is also verified. Now, we must use the same values. Okay, ID2 is coming out to be negative, meaning the diode D2 is off, meaning from the model itself, that should actually be equal to 0. But we still use that value to calculate ID3. Okay, we do not deviate from that until the analysis is complete. We cannot change our assumptions in the middle of our analysis. Once you pick an assumption, you have to stick with it till the end. Okay, so in this case, it turns out that our diode D3 is indeed on. But now we have to go back and we have to choose a different state. Okay, so I'm going to put an end to this right here. Let's see. Okay. All right. Now we choose a different state. And in this state, I will still stick with D1 as on, D3 as on, but this time I'm going to choose D2 as off. Okay, D2 as off. Now I have to redraw the circuit. Once I redraw the circuit, let's see what we get. Okay, so let's go ahead and copy, and I'll copy and paste it. Okay, so now I have D1 and D3 both on, so they are still the same. D2 is, however, off, and so I've replaced that with an open circuit. Note that the voltage polarities and the current direction do not change. Right? VD2 has the same polarity because the anode is on the left, so plus is on the left, and current always flows from anode to cathode, so it's going from left to right. Okay. Now we will analyze our circuit, and we'll see what we obtain. Okay, so we can apply, let's see, we can do KCL, we can do KVL, we can do Ohm's law. But this time, because we are saying that our diode is reverse bias, we need to see if VD2 is less than 0 or not, meaning VD2 should be a negative value. So we want to calculate VD2 voltage. So best course of action would be to apply KVL. So we apply KVL around the loops. There are multiple pathways, of course. We can go from here to here. We can go from here to here. We can also go from here to here. Okay, multiple pathways. So we will start with the one on the farthest left. We start with the one on the farthest left. We can write at the top, from the top, it's plus 10 volts right here, plus 10 volts, plus 10 volts. Then there's a voltage drop caused by IR1 and R1. And so it will be minus 10,000 IR1, 10 kilo ohm. Then there's a voltage drop of 0.6. Then there's another voltage drop across the resistor R2. So minus 10,000 IR2. And then finally, the negative voltage drop or negative voltage supply minus of minus 20 should sum up to 0. Law of conservation of energy, Kirchhoff's voltage law. If you have a preferred method of applying KVL, you stick with that. You do not have to use what I use. Again, everybody has been doing KVL and KCL for a while. So if you have, again, if you have a preferred method that you have been using for several years, you can stick with that. You don't have to do what I do. Okay, now, unlike the first circuit, if you look at this circuit, there is an open right here at diode D2. So all of the current coming from the top right here is going to flow through R2. So IR1 is the same as the diode current ID1 and is the same as the resistor current IR2. Okay, so I'm going to write that down here. IR1 is equal to ID1, which is also equal to IR2. There is no other pathway for the current to flow through, right? There is no other pathway for the current to flow through. It's all the same. So if you plug that into the above equation, we can obtain a direct result for ID1, right? We plug this into the above equation. The only unknown variable would be that current. And again, as we stated, that is the same as the diode current. And so we can find ID1 as 29.4 divided by 20,000. Simply rearranging the terms and obtaining the value. 1.47 milliamps. Okay. And again, this is from KVL in the farthest left loop, starting at the top, plus 10 and ending here at minus 20. And then, of course, the current through all of them is exactly the same. So IR1 is the same as ID1 is the same as IR2. We simply plug that into this equation and you solve for ID1. Okay. Okay. All right. So now let's go to the other side. What do we see? There's no other pathway for the current to flow through. So ID3 is the same as IR3. Okay. And that makes things simple because voltage at C does not change. That remains minus 0.6. Okay. So you apply nodal or Ohm's law across this, find the voltage at either end of R3. So it'd be 0.6. So minus 0.6 minus of minus 10, and we can find the current IR3. Okay. So I'm going to move from here to the right here to keep the circuit diagram in view. So I'm going to say ID3 is the same as IR3, which is the same as node C, voltage at node C, which is minus 0.6, and then minus of minus 10 volts divided by 10,000. And so current through diode D3 is 0.94 milliamps. Okay. So it is still correct. Note that the values are different. Look at it right here. Okay, values are different. We still don't know, not yet. We still don't know yet whether our assumptions are correct or not for this state. But in both cases, we have obtained a positive value, but the values are different. So different assumptions, different values. But in both cases, D1 and D3 have turned out to be true. Now let's apply a KVL that includes VD2. A KVL that includes VD2. Now, of course, we have a couple of different pathways. We can apply it here, or we can apply it here. Okay, a couple of different pathways. Either one is fine. Doesn't really make too much of a difference, but we have 0.6 volts right here, so we'll stick with that. It makes it easier. So we'll include the diode voltage drop VD3. Okay, so KVL that includes VD2. Okay, KVL that includes VD2. And so again, I start at the very top. I have plus 10 volts minus 10,000 IR1. And this time I have VD2. So minus VD2. And then minus 0.6 goes to ground, sums up to 0. Now we have two unknowns in here, VD2 and IR1. But we already have IR1 from here. And so we can plug that into this equation. And we are left with only one unknown, which is VD2. We solve for VD2. And let's see if we obtain a negative answer. If it's positive, if V2 is positive, then that means our assumption is still incorrect. We'd have to go back and choose another state. Okay. This is 10 minus 10,000. And IR1 in this case is 1.47 milliamp. So this would be 0.00147 plus 0.6. And thankfully, we obtain a negative answer. This comes out to be minus 4.1 volts. Minus 4.1 volts. And if this is negative, that means that my assumption that D2 is off is indeed correct. And there you have it. This is the way we would analyze using the ideal diode or the constant voltage drop model. The analysis using ideal diode model will be exactly the same, except that all diode voltages would be 0 volts. Okay. If you assume the diodes are on, there would not be 0.6. You would simply take it to be 0 volts. Everything else still remains the same. Reverse bias diode, negative voltages. Forward bias diode, a positive diode current. Okay. Our job is not quite yet done. The entire purpose, the main purpose of performing this analysis is to determine the Q points. And so the Q point for these diodes, or the analysis for these diodes, gives us, for diode D1, what do we have? Well, diode D1 is on, so of course the voltage is always going to be 0.6 volts. The current is right here, 1.47. So Q point gives me 1.47 milliamps and 0.6 volts. Diode D2 is off. So my current, of course, is 0 milliamps. And voltage we just obtained was minus 4.1 volt. And D3 is, what did we say we obtained for D3? 0.94 milliamps. It's a forward bias diode. And so voltage is 0.6 volts. And that is the complete analysis using the constant voltage drop model.